Welcome, fellow developers and tech enthusiasts. Today, we're diving deep into a game-changing approach to deploying Java microservices, accelerating the process with AI-driven Dockerization. Microservices have revolutionized how we build scalable and resilient applications, breaking down monolithic beasts into nimble, independent services. But as anyone who's deployed them knows, the complexity shifts. Instead of one large deployment, you now manage dozens, even hundreds, of smaller ones. This brings us to Docker, the ubiquitous containerization tool that packages our applications and their dependencies into portable, isolated units. While incredibly powerful, crafting an optimal Docker file for each microservice can be a surprisingly complex, time-consuming, and often overlooked task. This is where AI, specifically generative AI, steps in as a powerful co-pilot, ready to transform our deployment pipelines. Imagine an intelligent assistant that not only understands your Java application's nuances but also recommends the most efficient, secure, and performant Docker configuration. No more guesswork, no more manual trial and error, just streamlined, optimized deployments. We'll explore how this conceptual AI system works, highlighting its key components and demonstrating its transformative impact on your development workflow. Get ready to supercharge your Java microservice deployments. Before AI, the journey of manually crafting Docker files for Java microservices often felt like navigating a maze blindfolded. Developers would start with a basic from instruction, perhaps copying their JR file, and then quickly hit roadblocks. Choosing the right base image, JDK versus JR, slim versus full, was the first puzzle. Then came the challenge of optimizing image size, leading to bloated containers packed with unnecessary build tools and dependencies. Build times could stretch, frustrating developers with slow CI/CD feedback loops. Even more critically, security often became an afterthought. Running as root, exposing sensitive internal ports, or including vulnerable packages were common pitfalls. Each microservice often required a unique Docker file, leading to inconsistencies across a large application landscape. What worked for one service might not be optimal for another, or worse, could introduce subtle bugs or performance bottlenecks. This manual, error-prone process became a significant bottleneck, especially for teams aiming for rapid iteration and continuous deployment. The need for a more intelligent, automated solution became incredibly clear. This is precisely where the vision of AI-driven Dockerization emerges, promising to transform this manual pain point into an automated, optimized process. Imagine a generative AI tool that, upon receiving your Java project, doesn't just suggest a Docker file but intelligently generates one tailored specifically to your application's characteristics. This isn't about AI replacing the developer, it's about empowering them. The AI acts as an expert system, trained on vast repositories of Docker best practices, security guidelines, and performance benchmarks for various technology stacks, including Java. It understands that a Spring Boot application has different needs than a plain Java servlet. It can analyze dependencies, identify the optimal Java version, and even infer runtime requirements. The output is a highly optimized Docker file, not just a generic template, but a custom-crafted blueprint for your container. This paradigm shift moves Docker file creation from a manual, iterative task to an intelligent, automated recommendation, significantly accelerating your deployment pipeline. So, how does this AI magic happen? At its core, an AI-driven Dockerization system would begin by performing a deep analysis of your Java project. Think of it as an incredibly intelligent static code analyzer focused on deployment. It would parse your pom.xml or build.gradle to identify the Java version, framework, like Spring Boot, and all declared dependencies. It would then scan your source code structure to understand the application type, entry point, and even potentially identify specific runtime needs. This comprehensive analysis allows the AI to build a rich contextual understanding of your microservice. For instance, knowing it's a Spring Boot application immediately tells the AI about common port exposures, embedded web servers, and typical JVM requirements. This contextual awareness is crucial. It's what differentiates a generic Docker file template from an intelligently optimized one. The more data the AI gathers about your project, the smarter and more precise its recommendations become, laying the foundation for true deployment acceleration. One of the most significant and immediate benefits of AI-driven Docker file generation is the automatic implementation of multi-stage builds. This is a fundamental Docker best practice for Java applications that is often overlooked or incorrectly implemented manually. The AI understands that you don't need the entire Java development kit, Maven, or your source code in the final production image. It intelligently separates the build environment from the runtime environment. In the first stage, the build stage, it uses a full JDK image, like Eclipse Demurin 17 JDK Focal, to compile your Java code, download dependencies, and package your application into a lean JR file. Once that JR is produced, the second final stage kicks in. Here, the AI switches to a much smaller JRE-only base image, such as Eclipse Demurin 17 JR Focal, and only copies the compiled JR from the previous build stage. This dramatically reduces the final Docker image size by excluding all the unnecessary build tools, leading to faster pulls, reduced storage costs, and a smaller attack surface, a perfect example of AI applying advanced optimization techniques automatically. Beyond multi-stage builds, an AI-driven system excels at implementing other critical optimizations that dramatically improve build speed and image efficiency. Consider layer caching. The AI knows that pom.xml changes far less frequently than your source code. So, it intelligently sequences the copy pom.xml and mvn dependency, go offline commands before copying the rest of your src directory. This clever ordering ensures that Docker only rebuilds the dependency layers when your pom.xml changes, massively speeding up subsequent builds. Furthermore, the AI prioritizes lean base images. For runtime, it recommends a JRE-only image over a full JDK, saving hundreds of megabytes. It also intelligently sets up a dedicated, non-root user, like Spring, in our example, to run the application within the container. This simple but powerful security measure significantly mitigates the impact of a potential container breakout, moving from a default root user to a least privilege principle, enhancing your microservice security posture right out of the box. Security and performance are paramount for production-grade microservices, and an AI-driven Dockerization approach handles these aspects with expertise. For Java applications, the AI doesn't just provide a secure base image, it also recommends crucial JVM tuning parameters specifically for containerized environments. Values like XMS and XMX for initial and maximum heap sizes, or XX plus exit on out-of-memory error to ensure graceful failure, are automatically configured. Critically, it includes XX plus use container support, a flag that tells the JVM to intelligently use the container's allocated memory and CPU limits, preventing resource overutilization or underutilization. Furthermore, the AI inherently understands security best practices. It suggests running your application as a non-root user, significantly reducing the blast radius of any potential exploits. It also ensures that only necessary ports are exposed, minimizing the attack surface. By automating these nuanced configurations, the AI elevates the security and operational robustness of your Java microservices, making them production-ready from the start. Integrating this AI-driven Docker file generation into your CI/CD pipeline is where the true acceleration takes hold. Imagine a typical workflow. A developer commits code to the Git repository. This commit triggers your CI/CD pipeline, perhaps GitLab CI/CD in our example. The first stage, as usual, builds your Java application using Maven.